So the data that comprises a file, of course, have to be stored on the hard drive. And so as we recall, the hard drive itself physically is broken up into sectors. And the sector is kind of the smallest unit of information that the hard drive can access, that the hard drive controller can access. And then we have this sense of disk blocks, which are typically collections of sectors. So when we want to allocate space on a hard drive to store a file, we need to allocate those disk blocks to hold that information. So the question then is, well, how do we go about allocating the blocks? So we'll start by looking at the simplest way to do this, which is contiguous allocation. Using this scheme, when we want to allocate space to hold a file, we're going to ensure that all of the blocks that hold the information of that file occur contiguously. This provides very good performance in most cases, in particular because when you want to access the contents of a file, say you want to just read the contents of the file sequentially, you'll have to move that disk head to get to the appropriate cylinder that contains the first block of that file, and then the head isn't going to have to move very much after that because the disk is just going to spin underneath the head, and the blocks will appear continuously or contiguously beneath the head, and you'll be able to read the entire contents of the file, presuming that it all fits in one cylinder. So this typically gives you very good performance. In addition, if you had to do random access, so you wanted to get to a particular block within a file, then because you're using contiguous allocation, let's say you want to get to the 10th block, you would find out what the address of the first block was that held that file. You just have to add 10 to that, and then that would give you the address of the block you needed to get a hold of in order to get that logical block of the file right away. It's very simple. All you have to do when you're going to store the only metadata you have to record in your directory for a file is its starting block location, its number, and the link, that is the number of blocks that are used to store that file. Probably the biggest problem with contiguous allocation is external fragmentation. Basically, if a file grows in size over time, then you may have to move the entire location of the file to a different place because you have to find a larger contiguous series of blocks in order to hold the content of the file. And again, as I said, you have a real potential for external fragmentation as files are kind of moved back and forth around to different contiguous blocks. You're going to split up the free space of the hard drive into smaller and smaller contiguous sections. Usually that means that you're going to have some kind of a defragmentation process that you run later on. The book talks about that as compaction, but the idea is that you'll kind of have to take the hard drive effectively offline and then move the files around into different sets of blocks so that basically you cluster all of the allocated blocks together, leaving one large or a few very large contiguous sections of free blocks or unallocated blocks. So the scheme for mapping is quite simple. When you want to go from a logical address, remember the logical address is something like you consider each file has its first block, so block 0 for a particular file, and so on. But we have to get from the logical addresses that are relative to each file to an actual physical block address or sector address on the hard drive itself. Usually our logical address will then you'll be thinking of something like a byte location within a file, like I want to get to the 50,000th byte within a file. That's easily enough partitioned to a set of logical blocks and then an offset to kind of take up the last bit. So the conversion of a physical address, like a byte offset within a file, to an actual a logical address to a physical address is typically done like this. So we'll assume in our case here that the blocks are 512 bytes. Typically they're multiples of 512, but we'll just keep it simple in this case. Then we'll basically take our logical address. If we divide it by 512, then that should give us a block number, sort of a logical block number into where we need to go. So that is, you're simming every 512 bytes corresponds to one block. So if your overall address was 10,000, you divide 10,000 by 512, that'll give you some number of blocks you have to get into to get to the 10,000th byte. Then the remainder of that division, again divided by 512, that'll give you the offset within particular block you're trying, where that 10,000th byte is actually stored. And the diagram then kind of looks like this. You take the logical address, you divide it by 512, you take the integral divisor up here, that's going to be your block number, and down here you take the remainder that you're offset within the block. By the way, because this is 512 is a power of 2, you don't really even need the integer division. You can just look at the least significant 9 bits of the logical address, and that'll be our value Q here, the block number that we're trying to access. So if we're using contiguous allocation of disk space, then the directory for the overall drive might look something like this, where we have the names of the files here, and we use those somehow to access a particular entry in the directory, and then each file will have its starting block number, that is the first block, the actual physical block that contains the content of that file, and then the link, that is how many blocks do I need to store the information in that block. And you can see that the directory is mirrored over here in the diagram on the left-hand side. So this file count starts at 0 and extends for just one more, a total of 2 blocks. So this is going to be where the blocks that contain the contents of count are stored. And if you look at this file called tr, it starts at block 14 and runs for a total of 3 blocks. So here's tr kind of down here, and so on. So the scheme is quite simple. You can see that you've got some unallocated sections of blocks here. That's all the kind of the white ones in the diagram, but quite simple. Okay, so an alternative to the contiguous allocation is a linked allocation scheme. And in this case, what we're going to do is that we're going to basically have the blocks that comprise a file stored as a linked list, and each block that comprises a file contains a pointer, an address, to the next block in that file. So you might get a diagram that looks something like this. So every block has to set aside some number of bytes to hold a pointer and the address of the next block in the linked list, and then the remainder of the space of that block can be used to actually store the content, the data content of that file. And the wonderful thing about this scheme is that there's no external fragmentation at all, because you can always allocate a single block and you can tack it onto an existing file if you want to. There's no danger of having your free blocks scattered is no problem for us, because the linked list can basically jump around to any block that's on the hard drive. So we don't need any compaction, which is nice. No defragmentation or anything like that is required. We will need some kind of a way to still define free blocks if we want to allocate them. We'll talk about different techniques for free space management later on. We do have a potential reliability problem when we're using linked lists like that, in that if any of the blocks on the hard drive, any of the sectors go bad, then we might lose one of the pointers in the middle of one of these linked lists, these chains of blocks, and then the content of that file is effectively lost from that point on. So those weaknesses aside, the conversion of a logical address that is an offset, say 10,000 bytes into a file, to the physical address is again fairly straightforward. We're going to take our logical address, and we're going to assume in this case that each of our logical blocks is a 512 bytes, like in our previous example, and that it takes 4 bytes to store the address of a block on the drive. And so that means of each of the block's 512 bytes, only 508 of them can actually be used to store data. So if we take the logical address and we want to convert it to the physical address, we have to divide by 508, and that'll give us a number Q, which is the Qth block that we're trying to access in the file. And then, as before, a remainder, the modulus operation here, should give us an offset within that block to get to the particular byte we're trying to access. Now, the problem is, once we've got Q, we still have to chain through. We have to go through the linked list to get to the Qth block. There's no other way to do that. And this is really why linked allocation is not very efficient, because if you think about it, there's kind of 2 basic things you want to do. If you wanted to do a sequential access, that is, let's say you wanted to read, say, the first 5,000 bytes of a file, you can get to the first block easily enough, but then every time you had to get to the next block that you're going to read, you'd have to do potentially another head move. So one head move to get to the cylinder which holds the first block of the file, and then potentially another head move to get to each of the blocks that comprises a file. And obviously this could be very inefficient and slow. If you want to do random access, it's potentially just as bad, because if you want to get to, say, just want to jump into and get to the 10th block of a file, you're going to again have to go through the linked list, start at the first block and chain through, again possibly having a head move each time. So it can be quite slow. Here's a diagram taken from the book, which kind of shows how you might store a directory. So here in this case you've got the file Jeep, and in your directory you'd have to say, well, what's the address of the starting block of that file, and then what's the address of the ending block. Typically you have both, so you'll kind of know when you get to the end of your jumping through the linked list. So you'd start at block 9, you'd have so much data stored here. If there was another block needed, then one of the bytes on block 9 would be a pointer to the next block in the sequence, say block 17. If that was full, then you'd have a pointer in that block to the next block in the sequence, and so on and so forth until you finally got down to some kind of representation you store in a field in a block to indicate that that's the end of the linked list. The FAT tables are a variation of the linked storage technique. This technique was actually used by MS-DOS. And the idea here is that rather than, say, storing the pointers of the pointers to the blocks in each of the data blocks, so in this case you've got one pointer stored in each of the blocks, scattered around like this. In a FAT table, you take all of those references, all those pointers, you basically group them together in one location. So at the beginning of every volume of a partition, you set aside a number of blocks to just hold the FAT table. Otherwise, it's much like the linked list. You're going to be taking, instead of storing all the links that were previously stored one apiece in each of the blocks, now all those links, all the pointers are stored in the FAT table. So you can kind of see how that works. So you've got the FAT table. This is typically going to be stored on your hard drive. You load it into the kernel when you mounted the system. And here you've got your directory. You might have, again, the name of the file, and then associated with the name of the file, you'll have an address, 217. That'll be the address of the first block that comprises the file. So far, this is just like the linked list. But now here's the difference. The link to the next block is stored in the FAT table itself. So if you look at entry 217 of the FAT table, that entry is going to be a link, an address possibly, to the next block that comprises this file, i.e. the file test over here, say to block 618. The entry for that is going to be the address of the next block that comprises that file. Now, of course, to read the contents of the file, you'd have to actually go look at the actual block 618. That's where some data for the file would be stored. You'd have to look at block 339. You have to look at block 217. And those blocks actually only hold data now because the pointers to the next element in the linked chain of blocks that comprises that file all those links are stored in the FAT table. So, of course, the FAT table is going to have some empty entries here because if the blocks aren't allocated, then you could just put zeros in these fields over here and negative ones, whatever you want to put there. But that's going to have to indicate that those blocks are free. They're unallocated to anybody yet. This is not as fragile as the pure linked scheme because if you lose a single data block on the file in the hard drive, you're not going to break the whole chain because the chain is actually stored in the FAT table itself. You can always trace through it. Now you still have to protect the FAT table, but that's all centralized, so it's usually relatively straightforward to do that by, you back up the FAT table, you store a copy of it someplace, and that can work quite well. All right, a lot of newer file systems, kind of like we were just talking about before, because the contiguous schemes the performance is so much better, but they suffer from external fragmentation. A lot of newer file systems try to kind of get the best of both worlds. And one of those uses can use something called extents. An extent is just a contiguous block, a contiguous set of blocks. And when we're allocating memory for a file, you just allocate things in extents. So a set of blocks which are contiguous are all kind of allocated all at once. If that extent isn't large enough to hold the entire file, then you allocate another extent. And of course, you'd have to then chain the extents together, and you could use different link schemes to do that. But because the extents are typically consist of many blocks, the overall performance can be pretty good. So if you're trying to do a continuous read or sequential read through a file, you'll basically have to move the head to get to an extent, but then you'll just the head will stay there while the drive spins the sectors underneath the head, and you'll read the rest of that extent. If you get to the end of the extent, then you may have to move the head again, but you're just moving the head less often. So now the downside of that, of course, is again we're kind of reintroducing the problem of internal fragmentation because we're allocating the portions of the hard drive in these larger collections of blocks. So you may have wasted blocks inside of a single extent that way. So the third method for allocation we're going to look at is the index scheme. This is in some ways kind of like the fat table we looked at before, but now you're basically going to have a fat table for each of the files. Will have basically its own fat table. And the way that works in the simplest scheme is that for each file you specify one block to serve as the index table, and what that block holds, what the index blocks hold, is references, addresses, pointers to the data blocks. So basically if you want to locate a particular position within a file, you pull up its table here to find the third block. You'd index into this table, you'd get the address here. That would be an address to a particular data block that held the data that you're trying to access. So this way you can think about, again, kind of like the linked list, the linked addresses. The addresses we had in the linked indexing scheme, again, are kind of stored as the elements in index blocks. And the data blocks just exist by themselves. So kind of like the fat table scheme, but now each file has its own fat table. Okay, so here's a simple example of that. Also a diagram taken from the book. So again, we have our file called gpeer, and we store in it an address in the array, in our directory, and this is an address to an index block. So when you go to block 19, the contents of this are to be treated as an index block, i.e. these guys are all the addresses of the data blocks that comprise that file. So the first data block is at position 9, so that's this guy over here, and the second is at position 16, that's this guy stored over here. So it's kind of like the fat table scheme. You can think of it kind of like a version of the link scheme where you're basically just taking all the links and placing them or localizing them in one specific area. Now, in order to convert a logical address to a physical address, it's very much like the scheme we had before. You basically take your logical address and you'll go ahead and again, we're assuming here that we've got blocks of 512 bytes, and so our index block can hold, and again, each block address is 4 bytes. So that means our index blocks can hold a reference to 128 data blocks maximally, which means we can represent or store files of up to 64 kilobytes in size. Not very big, but we'll see how to make that bigger later on. And so what we'll do when we want to convert a logical address to a physical address is we'll just go ahead and divide by 512. That is the size of our blocks. That gives us this reference Q. That's going to be an index, a displacement into the index blocks. So you just use that as a displacement into the index block. Whatever you get the address that's there, that's the address of the data block. And the remainder of our division here is the offset within that data block for the data we want to get. You can also see that one of the problems with this scheme is that you're basically wasting 128th of your disk space just to store index blocks, and that's in like the best case, where every file is 64 kilobytes in size. The problem is you're going to have to allocate a block to serve as an index block no matter how small the file is. The file might consist of a single byte. You'd have, in that case, one data block which is holding that 1 byte, and one other block as the index block for that very small file. Now the big problem with that scheme is that, as we saw, we were limited in size to, say, 64 kilobytes. If the blocks are bigger, say 4 kilobytes, then you'd have bigger files, but you'd still end up with a maximum that you could reach. And what we'd like to be able to do is store much larger files. And so we need a little bit more complex indexing scheme. So what we'll do, sort of the simplest thing we could do, is you could have a linked list of your index blocks. So that is, again, if we had 128 pointers in each index block, if the block was completely full, then we would say, okay, well, the last pointer is going to be a reference to another index block. So the index blocks contain references to data blocks, but if they're completely full, the last, or the 128th entry in the index block, is a pointer to another index block. And that way you can kind of get arbitrarily large files. There's no limit on the size you could have. This does reintroduce our problem of the linked list scheme, where again you have some fragility, right? If one of the index blocks goes bad, then you've broken that linked list. And again, you have the other problems with the linked scheme where you got to move the heads around a lot. But that's the concept of an index block. Another technique other than the linked index scheme is adding more levels of indexing. So we'll just start by talking about dual level indexing. So the way this scheme works is that you have two different levels of index blocks. You've got a topmost level index block, and the pointers in that block are all pointers to index blocks, low level index blocks. The low level index blocks only have pointers to data blocks. And using this scheme, you kind of have a simple three level tree where you get the top level. One block is the top level block. Then you have the next level of tree is going to be the index blocks, the low level index blocks, and the layer below that is all the data blocks. You kind of have this three hierarchy tree. You work out the math. If you have 4 kilobyte blocks that can store 1024 4-byte pointers in the outer index, then that'll give you about 4 gigabyte file that you could store that way. Pictographically, it might look like this. So you've got a reference in your directory mapping a file to a particular block. That block is the outer index block or the high-level block. All the references in this block are references to low-level index blocks. So here's the low-level index blocks here. Each of the low-level index blocks, then, its contents point to actual data blocks that comprise the file. The conversion, again, fairly straightforward, just modular arithmetic. So if you take the logical address, again, an offset to bytes you're trying to find in a file, first you have to divide by 512 squared. That is, you've got to get rid of you have to get the address Q1 here. This is going to be the address of the high-level block you're trying to access. The remainder here is going to be then cascaded down. You split that remainder also into it. This will give you the address of the data block. And within the data block, the address of the index block, and when you're there, you can use that to reference the actual data block that you're trying to access. So a fairly straightforward scheme. Again, we're limited in size to how big the file can go if we're stuck with dual level. Of course, if we introduced a tri-level or a quad-level scheme, you could have larger and larger and larger files representative that way. That's the kind of question I might ask on an exam, by the way. If you use a 3-level scheme and the blocks are so big and a file reference is so many bytes, what's the maximum size file I can represent with that scheme? The UNIX UFS operating system actually uses a sort of a mixed scheme for storing its files. So this is something called the I block, which is the file control, what they call a file control block in Unix. And so you have a bunch of information, meta information about a block, about a file, like what's the mode, who the owners are, what the timestamps is, when was it last read, when was it last modified, that kind of thing. And a measurement of the total number of blocks it takes to store that file. For small files, you'll kind of see in this gray area here, and the blue at the bottom here as well, this is where the references are stored. So some amount of the file control block is set aside just to hold addresses to data blocks that comprise the file. If the file is very small, then this set of pointers may be sufficient to reference all of the data blocks that hold the data for that file. If it's a little bit bigger than that, then we can go to the single indexing scheme that we first looked at. That is, this is a reference to a pointer to a single index block. That index block, as usual, contains references, pointers to data blocks. If that's still not enough space to hold all the data blocks of a file, then you can go to a double indirect scheme. So this will point to a high-level index block whose elements point to low-level index blocks whose elements point to individual data blocks. And that'll give you a lot more. And if that's still not enough, then you can go to a triple scheme where basically you add another layer to this tree over here. And of course, you're exponentially increasing the number of data blocks that you can reference. So this scheme for Unix can actually represent very, very large files. All right, so performance. Well, the performance of the different allocation schemes is going to depend to some extent on the kind of file access that you're typically doing. If you know you're going to be doing a lot of sequential access to a file, that may lead you to want to prefer a certain kind of allocation technique. But if you know you're doing a lot of random access, that might leave you in a different way. And then, of course, you have to worry about external fragmentation. Are you willing to suffer from external fragmentation? External fragmentation is okay, provided you can have enough downtime to defragment the drive, but maybe you're in a situation where you can't afford that time. So in that case, contiguous allocation might not be good. If just overall performance, speed is all that matters, the thing that matters most to you, then contiguous accent is the way to go because it provides the best sequential and random access. And again, the thing we're primarily measuring here is the number of head moves. So contiguous allocation will give you the fewest number of head moves in order to either do sequential or random access. Link schemes are okay for sequential access. You'll have to do a head move as you sort of scan your way through the file, but that's maybe not so bad depending on the throughput, how fast you can move the data from the hard drive to the CPU. So it's good, it's not great. It's terrible though for random access because the random access, the runtime of a random access is going to be proportional to how far the access is into the file. It may be that the operating system might want to ask the user to declare when a file is created whether that file is going to be needed primarily to support contiguous access or linked access. Maybe you've got some feel about what's going to be best for you as a file. So that's a possibility. Index schemes are more complex. They are in some ways more flexible. They allow for clustering as well. So, it's different things here. Contiguous is the best in general, but leads to external fragmentation, and the other schemes all have their pluses and minuses. One thing to consider is that because I/O is so slow, disk I/O is so slow compared to CPU, it can be worth spending thousands of instructions, tens of thousands of instructions, CPU instructions, in order to save just one disk I/O. So maybe there's some technique you can use to try to analyze the upcoming I/O requests. Again, caching is going to be important with this, and buffering will be important, but it's worth spending CPU cycles to avoid disk I/Os. And just as an example here, if you take a sort of a standard CPU from 2011 and it's clipping along at about 159,000 million instructions per second, a typical disk drive gives you 250 I/O operations per second. So if you take this millions of instructions per second, you divide it by the I/Os, you can see that you can afford about 630 million instructions can be spent during just one disk I/O. So if you're spending fewer than 630 million CPU instructions in order to avoid one I/O operation, one disk I/O operation, you've made a savings. And of course, you hope it's not going to be that big. If you're working with a fast solid state drive, those are much, much faster than hard drives, but still, so they're doing 60,000 I/O operations per second as opposed to the 250 we had above. But still, that means you can afford to spend up to 2.65 million instructions, machine instructions, to avoid one disk I/O operation, and you'd still win in that case. All right, so the next thing to talk about is free space management. So we've talked about different allocation, but we need a way when we're allocating blocks for a file to know which blocks are available, which ones aren't being used by a file currently. And this is typically done via some kind of a free space list. There's different ways that this information can be encoded. One of the simplest ways is through the use of a bit vector or a bit map. That is, what we do is we just we have a single bit that represents each of the blocks on a drive, and we could just go ahead and set the corresponding bit for that block to be 1 if that block is free and 0 if that block is occupied. So if you had n blocks on a hard drive, then you'd need a bit vector of n bits. And it's a relatively easy to find chunks of free space this way, because remember, if the blocks typically we're accessing the contents of our bitmap a word at a time. Words usually like 4 bytes or something like that. And most machine code languages provide an operation which can tell you if a word is 0 or not. So it's very easy for us to scan through the bit vector and finding blocks that are not all zeros, that is, which have at least one free block represented in them. So you could pull that out. And then finding offsets within those is also typically very easy to do. Most machine code languages provide an operation to return an offset to the first non-zero value in a word. So fairly easy to use. It does, of course, require space. You have to store the free bitmap someplace. Here you can see, well, if the block size in our hard drive is, say, 4 kilobytes, that's 2 to the 12th bytes. Our disk size is 1 terabyte, 2 to the 40th bytes. Then the size of our bit vector is going to be about 256 megabytes. Well, it's pretty big, but not that big compared to a terabyte. If we are clustering our blocks into blocks of 4, that is, we only allocate them in blocks of 4, then that's going to decrease our free bitmap vector down to only 64 megabytes of memory. It's still relatively small, terabyte, 1,000 gigabytes. This is a quarter of a gigabyte, so relatively small proportion of the hard drive space is used to store our free bit vector that way. Another thing we might do is we might store our free space as a linked list. So you might, kind of like we had in our link scheme, you might have a reference to just the first free block in the hard drive, and then each block would have a reference, a pointer to the next block that was free in the hard drive, and you can just chain through them. In that case, you're not wasting any space. There's no overhead like we had for the bit vector. On the other hand, it is fragile. If one of those free blocks goes bad for some reason, the sector goes bad, then your chain of free blocks is broken. You can usually restore that by scanning through all of the files and remapping out which blocks are allocated and which ones aren't allocated. You can probably rebuild the linked list, but it can take some time. So here's what here's the diagram from the book that shows what the linked list approach to free space management would look like. So again, all you have to do in the kernel, you have to store the address to the first free block. Each of the free blocks is a pointer to the next free block on the hard drive. Again, in terms of protecting your free management, a couple things you have to worry about. You have to always protect, no matter what, a pointer to the beginning of the free list. So you probably would want to store that on the hard drive in multiple places so that if one of the sectors that holds that pointer goes bad, you'd still have a copy of it someplace else. If you're using the bitmap approach, then you're going to have to make sure that that stays safe. Maybe you want to keep a duplicate copy of that in case something goes bad with that one of the sectors that comprises the bitmap. Another thing you have to watch out for is because of a caching situation, you want to be very careful that the kernel's copy of the bitmap doesn't differ from the hard drive copy of the bitmap in such a way that the kernel thinks that a block is free when the hard drive thinks it's not free. That could be bad. So there's different schemes you can do for avoiding cache incoherencies like that between the bit vectors. Another thing we can do is we can use grouping and counting to basically try to minimize the size, the amount of information, the amount of disk space we have to set aside to store our address of blocks. Again, this is kind of like the clustering scheme we looked at before in terms of trying to cluster information together, so we basically need less overhead to store information. One of the things we get with contiguous allocation is that as files come into existence and go away, as we move them around, the disk will tend to fragment more and more. one of the things you can do is you can count the number of times you've the number of times you've freed and removed disks, files, and you can use that information to kind of decide when you want to run a defragmentation algorithm. You can also try to be careful about your allocation of contiguous blocks. Always try to make them adjacent to each other as much as possible to minimize the number of holes, that is, the number of free sections of memory that you're creating. So try to keep that all clustered together. So there's different kinds of clustering techniques that can be used to try to improve the overall performance of your free space techniques.